with another type of sensor that we, let's say, anticipated. And then in many ways it is quite similar to an accelerometer from the point of view of at least the technology and partly the physical principle, so that they go well together, is the gyroscope. Okay, so the gyroscope measures a different thing. Actually, it measures the orientation in space. And typically, it does it in 3 dimensions. So I receive, let's say, 3 signals at the output of the gyroscope, which tells how the system is oriented, okay, with respect to a fixed reference frame. So the main application of gyroscopes is for navigation, and that is the traditional application of gyroscopes. Of course, the alternative to gyroscopes for navigation is the compass, la bussola in italiano, but of course the compass can be used only only when one can, let's say, measure the geomagnetic field. So in situations in which one cannot use the geomagnetic field, one typically cannot use a compass but uses the gyroscope. So basically it's necessary when the geomagnetic field cannot be used. And this means, for example, in space, that was traditionally one of the first uses, or on planes, also because in the case of planes you also need a 3rd dimension, while the compass gives only you 2 dimensions. Of course, in a plane you need to know whether you are let's say in this direction or in this other direction. Okay, and this is something that the compass cannot give you. And then, for example, also in tunnels, because in tunnels you typically have a distortion of the geomagnetic field because of the presence of rocks and of metals, and therefore the compass is not reliable. So this is basically the traditional use of gyroscopes, even before MEMS gyroscope were usable. So before MEMS, you remember, stands for macro electromechanical systems. They're systems fabricated with semiconductor technology. But before this technology, there were other means to fabricate gyroscopes, very expensive actually, but used for space applications and airplanes applications. The other uses which are very common are for stabilization. For example, stabilization of cameras, a typical use in digital cameras and in smartphones, and for robotics applications, in order to control the movement of a robotic arm. For example, you need to know exactly how the body is positioned in space. Okay. Since the technology for gyroscopes is similar to the technology for accelerometers, they are typically sold in the same system of package, so on the same chip. You see both the gyroscopes and the accelerometer, and they call it a 6-axis accelerometer slash gyro. Okay, 6 axis because 3 is for the acceleration and 3 is for the orientation. So 3 axis accelerometer plus a 3 axis gyroscope. This would be 3D plus 3D means 6 dimensions. I mean, the system is called SOP, which stands for System on Package. The meaning of System on Package is that basically you have the same package and typically at least two different dies. If you remember, so 2 different pieces of silicon, and typically you have one for the sensor and one for the electronics. Because even if the technology is the same, the process of course is not exactly the same, and you fabricate on a different wafer the sensors and on another wafer the electronics. And typically in this case you have sometimes one die for the accelerometer, one die for the gyroscopes, one die for the electronics. They are put in the same chip package. Okay, let's consider the principle of operation of a gyroscope, and it's basically a very basic physical law, which is the conservation of the angular momentum. Oh, let me state it again because it maybe some time has passed since you last saw it. It says that the total angular momentum of a system with respect to a fixed point is constant if no external force acts on the system. So one consequence of the conservation of angular momentum, which is actually usable in order to obtain a gyroscope, is the Coriolis force. The Coriolis force is a so-called inertial force which emerges in a reference system rotating with respect to a fixed reference system. Okay, so what are we talking about? The main, let's say, words in this definition is inertial force. By means of inertial force, we mean apparent force, okay? It's not a real force. In inertial force in Italian it's called the forza apparente, which means that it is a force that you only see because you are on a system which is not moving at a fixed constant linear velocity, okay? So, actually the Coriolis force in particular appears if this system is rotating with respect to a fixed reference system. And let's see how it works. Let's assume that we are in a fixed reference system. I don't want to derive all the equation, but I want you to, let's say, understand the main principle of operation. And basically, I just draw a comic, very simple comic. The time passes in this direction, and let's assume that there is a body, a rigid body, which is rotating. So, in order to, let's say, highlight the rotation, I draw a square, which is rotating around this point with an angular velocity that we called omega. So this is the square at some point, at some time. So then after some time it has done some rotation with respect to this fixed point, and after some other time it has done another angle, so it has continued the rotation. Okay, this point is fixed. Let's call it O. So the square is rotating. Now, imagine that inside this square there is a body, there's a mass, for example, that is moving with constant linear velocity towards the upper side of the screen, so in this direction. Okay. Now, if I draw everything at the different time frames, what happens is that, of course, this is not rotating. So the rotation of the square does not mean anything for this mass, right? So it's moving only in this direction, then it would be here, and then it would be, let's say, here. No, maybe a little bit higher. Let's put it here. Okay, so it's only moving in this direction. It's not influenced by the rotation of the square. Now, if we considered exactly the same thing with respect to the rotating reference system, something happens. Now, I'm now considering a reference system which is fixed to the rotating body. Okay. Now I see the rotating square as fixed in time, right? So I see it here. Now it's here. And now it's here. Okay. And the point is that apparently, with respect to this fixed rotating system, the mass is moving in a strange way, because it is, no, let me just put the symbol. Now it is here. This point appears to be here, right? So it was here, and then it's here. And this point appears to be something like here. So it basically behaves like it's moving along a curved trajectory. So we have an apparent curved trajectory. In order to have an apparent curved trajectory, you need a force acting on the particle, which is of course an apparent force because it is only seen if you are on this rotating reference system. So one can say, okay, the velocity, the relative velocity of the body is instant by instant along this trajectory, and of course in order to have a curved trajectory you need to have a force which is acting perpendicular to the velocity, and this is the Coriolis force and the Coriolis acceleration. This is the Coriolis acceleration, which is of course proportional to the force by means of the mass of the body. Okay, so I don't want to let's say demonstrate the expression for this Coriolis force, but there are a few things which are let's say evident. One is that in order to have a curved trajectory, the Coriolis force must be perpendicular to the relative velocity of the body in this rotating reference system, and therefore you have a vector product, and then it's also proportional to the rotation velocity of the system. So again, if you see for what I have described, you have an apparent velocity in this direction. You have let's say in this direction along the blue line, you have the vector of the angular velocity which exits out of the screen, and therefore you have the Coriolis acceleration as let's say in this direction as resulting from the vector product. And the proportionality constant is 2. Okay, so I'm not demonstrating this, but I need to, let's say, stress this aspect. Why this is important? This is important exactly because we want to measure the angular velocity in order to understand the orientation instant by instant, and we transform the angular velocity into an acceleration using the Coriolis force because we know how to measure an acceleration. We have seen we can do it with an accelerometer. So basically we are adding another transduction. We will pass from an angular velocity to an acceleration, from an acceleration to a displacement, from a displacement to a difference of capacitances, and then to a voltage. So we already know the last steps. We only need to understand how we can exploit the Coriolis force. And it's basically very simple because this is something which does not need a real system because it's already, let's say, in the physical world. If we are on a rotating reference system, so for example, if the sensor is fixed onto the smartphone, we can sense an acceleration when the smartphone is rotated in direction. When we move when we change the orientation along each of the 3 axes. So the only thing that we need to consider is how we distinguish the measurement of an acceleration from the measurement of a rotation, because of course we have both. And the thing is quite simple. Basically what we do is the following. Let's assume this is the reference rotating system, which is let's say fixed to the smartphone. If we consider always this example, this rotates in this direction, okay? And then we have 2 masses here. Instead of 1, we need 2 masses. which must be identical. And now we have to apply some velocity to these two masses in order to obtain the Coriolis force. And in order to have some velocity, we put these two masses in vibration in this direction. Okay, for example, we apply at the given instant a velocity in this direction. Two velocities must be in the same direction, but in the same direction, the same quantity, but opposite direction, opposite sign, let's say. And of course, we apply vibration because we cannot apply linear movement. We need to keep everything very contained in space. So let's consider this a snapshot. We apply this velocity at a given time, and of course we observe a Coriolis acceleration. For what we have described, I have the velocity, for example, for the first, I have the velocity, I have the movement, the rotation axis, and then I have the Coriolis force in the vertical direction. So there's a force and therefore an acceleration acting on this mass in the vertical direction, and on the other mass in the opposite direction. And of course, in order to measure the acceleration, I have to put a capacitance with moving plates. For example, here I call it C1, and here I call it C2. These two accelerations in opposite directions will give me a displacement in opposite direction, and therefore will change the two capacitance in opposite directions again. So I can use exactly the same circuit that I've shown you some minutes ago in order to transform this variation of capacitances into a voltage. So I will have that C1 minus C2 is going to be proportional to the rotation. So I know how much everything has been rotated. So, of course, if I know instant by instant the angular velocity, I can know the orientation in time. I can integrate and actually know the orientation. Okay, so you see, I'm not spending much time on it because it's exactly the same principle of operation of an accelerometer once we have understood how the Coriolis force operates. The only thing that you need to consider is that we need to distinguish the angular velocity from an acceleration of the whole, let's say, platform along, for example, the vertical direction in space. And the thing is very simple. If there is a linear acceleration, the two masses move along the same direction, and therefore the difference between C1 and C2 does not change. Okay? If I want to measure the acceleration, I need to consider only one moving mass and check the displacement of this mass between the bottom plate and the top plate with the capacitance difference. If I want to measure a rotation, then I need two masses, and I need, because in the case of rotation, this C1 and C2 between the two masses and, for example, the same bottom plate are varying in opposite direction. So, and therefore I can distinguish between a linear acceleration and an angular velocity. If the system has a linear acceleration, let's call it AL, for example, in this direction, then AL x equally on C1 and C2, and therefore C1 minus C2 is 0. So this difference is only sensitive to a rotation, to an angular velocity, and not to a linear acceleration. Okay, so, and this is the reason why we use two masses here and not just one. Okay, because with only one mass we cannot distinguish between a linear acceleration and a rotation, because we observe exactly the same thing.